Morning, all of you. That day we were seeing SN2 mechanism. For SN2 mechanism, there should be no steric hindrance or less steric hindrance. This was our alkyl halide. When OH comes from the remote side, OH comes from the remote side to attack. All these hydrogens will be turned to all these hydrogens will be turning to the other side. That is OH, C, H, H, H. We call it as this inversion of configuration. Just like an umbrella in a strong gale, the odd or H groups are going to the other side. So we say inversion of configuration. Inversion of configuration. In SN2 mechanism, inversion of configuration takes place. Now, you consider another compound where these groups are bulkier groups. These are bulkier groups. Where this is a CH3, this is a CH3, this is a CH3. Now, OH will not get space to attack from the remote side. OH cannot attack. OH will not get OH will not get the space to attack from the remote side. So what we have to do? You have to put this substrate. This is the substrate and this is the reagent. This is the reagent. OH minus is the reagent and starting material, that is the substrate. You put this in a polar solvent. Polar solvent means water H2, polar solvent. Polar protic solvent means protic solvents means you can protic side can take away the Cl minus very easily. So polar protic solvents. Polar protic solvent. Put this in a polar protic solvent so that Cl minus will get detached and this carbon will get carbon along with its CH3 groups will get detached. So what I am getting is C. C. Now it is a C plus. A C plus is going to be formed. We know that C plus is planar. Last year we learned C plus is planar and it will be having vacant p orbital. It will be having a vacant p orbital because around the C only 3 bonds you are seeing now. So those 3 CH3 groups will be standing far apart in 120 degree, and the C plus is formed with a vacant p orbital. With a vacant p orbital. Now, first step is over. The second step is the attack by the nucleophile. I told you OH cannot come from the remote side. It cannot come from the front side also. Why? Because front side the Cl minus is there. So from front side it cannot attack. From the remote side also it cannot attack. So by SN2 mechanism, the reaction is not possible. So we are putting this in a polar protic solvent. By putting in polar protic solvent, a carbocation is produced. This carbocation, see, all the groups will be at 120 angle. So it is flat. Now OH can attack. OH can attack from the front side or from the back side. Front side in the sense in front of this board or from the back side of the board. So two possibilities. Now OH minus has got two possibilities. It can attack from the front side or it can attack from the back side. If it attacks from the front side of this side, if it attacks from this side, all CH3 groups will be going to the other side. Or it attacks from the back side, then all CH3 groups will be coming to this side. That means two types of configuration you are getting. So here, if it attacks, so I am writing it again, this is step 1. This is step 1. Step 1. What is step 2? Step 1 starting from where? That is C. I am writing the same thing, C plus CH3, CH3, CH3. Take the p orbital. If now OH minus attack. Now OH, if it attacks, then two possibilities are there. Front side attack, back side attack. So front side, you can consider the CH3 like this, one CH3 like this, one CH3 like this. Means one CH3 like this, one CH3 like this, and one CH3 like this. OH can attack from the front side or OH can attack from the back side. If OH attacks from the front side, all CH3 groups will be turning to this side. If OH attacks from this side, all CH3 groups will be going to the other side. So, you are getting two configurations. That is OH, half of the molecules, probability 50-50. So half of the molecules will be taking this and the other half will be taking equal probability. This is called, it is retaining the original configuration. This is retaining the original configuration. So we call it as retention. We call it as retention. While the other one, that is got inverted, just like that SN2, the other one is inverted. Inversion. Retention and inversion configuration. Now, this is the SN1 mechanism. Here a carbocation is formed. A carbocation is formed means if the carbocation is a good carbocation, then the product will be formed from that carbocation. If it is good carbocation in the sense, if it is a stable one. If it is an unstable one, then the product will not be made or less amount of product will be formed. We have to check what the stability of carbocation. What is meant by the stability of carbocation? Last year we learned by hyperconjugative effect. 3-degree carbocation is more stable than 2-degree, which is more stable than 1 degree. This year, that hyperconjugative effect we will not be using. Instead, we will be telling the term inductive effect, inductive effect, inductive. So this year I will tell you this carbocation, a 3-degree carbocation is stable due to the inductive effect. Means the electron pushing effect of CH3 CH3 is an electron donating group. Inductive effect of CH3 means it is an electron donating group. By donating this electron to the C plus, the lifetime of C plus is increased. That means the stability of this carbocation is increased. So 3-degree carbocation is more stable than a 2-degree carbocation, which is again more stable than 1-degree carbocation. So the order of SN1 reaction is 3-degree greater than 2-degree greater than 1-degree. So this is the mechanism of SN1 reaction. What is the stereochemistry based on this SN2 and SN1 reaction? Stereochemistry means whether it is in the retention position, whether it is an inversion position. Before that, let's go to different types of carbocation. We know that 3-degree carbocations are more stable due to inductive effect. 3-degree carbocation is the most stable carbocation due to the inductive effect of 3 CH3 groups. The carbocation we call it as tert-butyl carbocation. Carbocation you can show like this also. This is called tert-butyl carbocation. Tert-butyl carbocation. This is more stable than secondary. It is more stable than primary. Now another carbocation is allyl carbocation. CH2. Double bond CH, CH2C. Now from this, there is a possibility of formation of a stable carbocation. This will be going that way only. In what way it can move easily? In what way it will break? That depends upon the form product. That depends upon the form. Going to a place you can stay very well means that place. Our movement depends upon that place, whether that place is suitable for our living or for our life and all. We want to go to a place where it is comfortable for us to live. So we will be moving to that place. So our movement depends upon that place. This movement depends upon the stability of that carbocation. So here, if it breaks, what happens? You will be getting a stable carbocation. How? By resonance. So CH, double bond, CH, single bond, CH2 plus, and Cl minus. Cl minus. Now, we are not interested in Cl minus. We are looking at the stability of carbocation. That carbocation is stable. How? By this shift. This shift, there double bond will be coming. This carbon is losing, it will be having a positive charge. It will be having a positive charge. So, from this step to the other step, it can be writing resonance structure here. Resonance structure is CH plus CH double bond CH. This is number 1. Number 2 resonance structures. It is resonating from this to that, that to this to that, that to this. That means this resonance gives stability to the carbocation. Tertiary carbocation is stable by what tertiary carbocation is stable by inductive effect. But this allyl carbocation, we call it as allyl carbocation. Allyl carbocation is stabilized by resonance. Anyway, it is a stable carbocation. If it is a stable carbocation, the mechanism will be SN1. Mechanism will be SN1. One more carbocation, that is benzyl carbocation. Benzyl carbocation. What is benzyl carbocation? This is benzyl chloride. This is benzyl chloride. On breaking, it will give a stable carbocation. How? We will see. So here, I am writing a benzyl carbocation, CH2. This benzyl carbocation is again stabilized by resonance. How? This will be shifting here. So this carbon is on loss. This carbon no profit, no gain. This carbon is gaining. There the electrons are coming. So this will be double bond and this carbon will be positive. So this is the second structure. Now this bond will move here. So this carbon is on loss. This carbon no gain, no profit. This carbon is gaining. So positive charge will be captured. This is the third structure. One more rotation you can see. This bond can come here. So that will be a double bond. This carbon is on loss. This carbon no profit, no gain. This carbon is on gain. And this can shift here. So you will get another resonance structure. So 5 resonance structures are available. As more and more resonance structures available, the carbocation becomes stable. Carbocation becomes more stable. So benzyl carbocation is stabilized by resonance. Tertiary carbocation is stabilized by inductive effect. Allyl carbocation is stabilized by resonance. Benzyl carbocation is also stabilized by resonance. So these compounds, these benzyl chloride, allyl chloride, tertiary butyl chloride, these all will undergo SN1 mechanism. All of you write the resonance structures of this benzyl carbocation once again. Benzyl carbocation once again. Next, CH2 double bond CH. Final is vinyl chloride. Vinyl chloride does not undergo substitution reaction, whether SN1 or SN2. Vinyl chloride does not undergo substitution reaction. Why? Because vinyl chloride to make a substitution reaction either by SN1 or SN2 is ultimately broken finally. Whether it is outgoing group or whether it is in the minus state or whether it is in full delta minus state or full minus state. Some minus should be created over there. This bond is to be long and in the case of SN2 mechanism for the easy flow cleavage, this bond is to be more pulled away so that the bond length becomes more and finally break. But in this case, bond will not be elongated. Why? Because due to this resonance, there are a double bond characteristic is. So, see it. This it's double bond single. It has got a partial double bond character, so this bond will not be broken. So, vinyl chloride does not undergo substitution. The SN1 or number one, number two, which will undergo SN1 reaction faster. This will undergo SN1 reaction faster because it is a secondary carbocation that will give only a primary carbocation. Secondary is more stabilized by inductive effect of alkyl groups can give electrons. So the secondary will undergo SN1 reaction fast. SN2 reaction which will undergo, this will undergo SN1, SN2 reaction faster because there is less steric hindrance compared to this one. Which will undergo SN1 reaction faster. That will undergo SN1 reaction faster, then secondary will undergo, then primary. SN2 reaction, primary will undergo faster, secondary slow, tertiary slow due to the steric hindrance around that carbon. That is, see, delta plus. There will be steric hindrance on this positive nature carbon. So SN1 reaction is just opposite that of SN2 reactions in the case of their speed of the reaction or the rate of the reaction. In SN1 reaction, there are two steps, while in SN2 reaction there is only one step. SN2 reaction is a single step reaction attacked by the nucleophile and the cleavage of that outgoing group These are taking place at the same time. But in the case of SN1 reaction, first step and second step. First two steps are there. First step is the slow step and second step is the fast. So here, slow step, we know that we learned that the rate of reaction depends upon the slowest step. The first step is the slowest step. So rate of the reaction depends upon only that step. There only one substrate is there. So SN1 reaction follows what its concentration is affected on this rate of the reaction. So in SN1 reaction, we say it is a first order reaction. Why? Because only the concentration of substrate on that alkyl halide is considered. In first step, there is no reagent, there is no OH minus. So it is a first order reaction, while SN2, both the concentration of the alkyl halide as well as the concentration of OH minus are considered or are affecting the rate of the reaction. So SN2 follows second order kinetics, while SN1 follows first order kinetics. And in SN2, two molecules are colliding, so it is a bimolecular reaction. And SN1, it is a unimolecular reaction. So here, SN2 and SN1, what are the differences between SN2 and SN1? It is that we will do in next class. Thank you.